Good morning, everyone. So we're now ready to start our new seminar at the IAC. Today we have Guillaume Thomas. Guillaume Thomas, he's a Juan de la Cierva Fellow, Junior Fellow, who defended his PhD in Strasbourg in 2017. That is almost about 4 years ago. Then he has spent his first postdoctoral stay at Victoria, British Columbia, at the observatory as a National Research Council Fellow. And since August last year, since August 2020, he's a fellow, he's, as I said, a junior Juan de la Cierva fellow at our institute. And today he will be talking about reconstructing the history of the Milky Way and proving the dark matter nature in WEAVE and LSST era. I remind the audience that I will mute everyone but the speaker from now on until the end of the talk, and that questions can either be written in the chat or I will unmute people and people can raise hands at the end of the talk. Okay, so all yours, Guillaume.
Okay, well, thank you very much, Carlos, for this kind introduction. As Carlos said, today I'm going to present you a part of my work that I did over the last years, which was to reconstructing our history of the Milky Way and to probe the nature of the dark matter itself. And especially, I would like to introduce to you what are we going to learn in the future with the new generation of surveys, whether astrometric, photometric, or spectroscopic. So especially speaking about WEAVE, which is something local, and LSST as well, and other surveys on which I'm part of, which is kind of equivalent to LSST. So at the end of the talk, what I would like to convince you especially is that distances is something which is extremely important to get. It seems to be kind of easy to get. It's one of the things that can sound obvious to obtain, but however, you will see that it's not as obvious to get them, especially to study our galaxy in general. So on this first slide, you can see the Milky Way taken from different areas. So you can see clearly actually that corresponds to the places where I used to live and where I used to work. So from Strasbourg, Victoria, and the Canary Islands. So my conclusion is just I'm going to places where you can see better and better the Milky Way. So when you speak about our galaxies, the best picture actually to take is our closest neighborhood, the Andromeda galaxy, which is often presented as a twin of our own galaxy. So you see really clearly these galaxies that have been used for one of the Star Wars, for example. So when it says it's a really far away galaxies, not really true. Anyway, so since I saw this picture when I was a child in a book, I starting to wonder, is that possible to get something, so structures in the nature, or is that possible that nature makes something, so structures like look like a pancake when you start with a universe which is initially almost homogeneous? And so since that time, I'm wondering, is it possible that such a galaxy was formed? And then, is that going to evolve? Is that something which is stable? And if not, is that going to evolve? So these two questions are related to two different fields. The first one related more to galactic archaeology, which is to understand how was formed a galaxy such as ours, what has a different mechanism to build it, what has the different building blocks, can we reconstruct it? And the other, which is to know, is that going to evolve, relate more about galactic dynamic. But actually, these two fields are really closely connected together because, as you know, in the lambda CM paradigm, but also in other paradigm, like in MOND, for example, the structures such as our galaxy are formed hierarchically through a succession of mergers of smaller galaxies that have been accreted and make the galaxy growing bigger and bigger. So I used to call myself as either a galactic archaeologist or galactic dynamic, but preparing that talk, I'm realizing that I'm maybe more a galactic surveyor, trying to get distances and to measure the morphologies of our galaxy, especially. So here it is a video of a formation of the galaxy, which is the best way to understand our galaxy formation is to go back to cosmological simulation and just to see what's happened to make such a galaxy like the Milky Way. So I hope you can see it. No, oh. Okay, well, anyway. So normally on this video, you will see galaxies merging together, forming this kind of big structure at the end. which will be like galaxies. So you will be different structures that you can already start to see here with shells. Oh, there it is. No, whatever. Anyway, so yeah, so you can see normally some dwarf galaxies here, some streams, and actually the streams here are made by the disruption of a dwarf galaxies, which is a tiny fluffy ball that have been perturbed by the tidal effect produced by the host galaxy. In our case, is the Milky Way. And this deformation at some point becomes so much important that the stars are going to escape through the Lagrange points of the dwarf galaxies on making these thin stellar structures that you can see there, which are actually stable over many giga years, especially coherent. And at some point, due to the phase space generated by the passing of all the dwarf galaxies, of all the mergers, these structures are going to disappear to make something which is smoother as a smooth component of the halo. But also, however, they keep their position in phase space for many, several giga years. So the best way to study our galaxies is actually in the outer part of our galaxy, especially in a component called the stellar halo, which is the outermost component of a galaxy, with a size typically 15 to 20 times bigger than the size of the disk, as you can see here on the Andromeda galaxy from a survey called PANDAS that have been used to observe the stellar halo of the Andromeda galaxy of the triangular galaxy. So actually, we think that the stellar halo goes up to the virial radius of the galaxy. So here you just see half of the stellar halo in radii. So you can imagine something really bigger. So as I was saying, the stellar halo is mostly composed is mostly made by accretion of other smaller galaxies, such as dwarf galaxies or even globular clusters. And so the stars that compose the stellar halo have the same properties as in their initial progenitors. And so they are, for most of them, old metal poor and distribute all around the stellar halo. One of the things also that you can see when you observe all the stellar halo of the Andromeda galaxy or the one in the Milky Way is that you can see you have plenty of substructures, either dwarf galaxies, globular clusters, or stellar streams that have these thin structures there. So we see plenty of them. And actually, this kind of objects are extremely precious because they are the direct recording of the accretion history of our galaxy. Therefore, by studying their properties and the dynamic, we are able to reconstruct our galactic origin, but also in the stellar halo, the mass of the stellar halo is only accounting for 1% of the total stellar mass of the galaxy. So which means that in terms of fraction of masses, it is negligible, especially when you compare to the density, because you have 1% of the mass of the disk typically, which is on a volume which is 1,000,000 times bigger. So it is meaning that in the outer part, actually, what is dominating the dynamic of the stars is the dark matter distribution. Therefore, if you can measure the velocities of the stars in the stellar halo on in the substructures, you can measure what is a galactic potential, and so go back directly to the measurement of the dark matter distribution in the galaxies. Moreover, some of the structures, such as the stellar streams, can also help us to probe the nature of the dark matter, especially by probing the granularity of the halo itself. So why it is really important to reconstruct the accretion of our galaxy in particular? Because, as you know, we have plenty of galaxies in the universe. So why is that so interesting to study our galaxy? So first of all, I would like to say there's something anthropological. We would like to know where are we coming from. I think humanity always try to do this. So it's important to know where are we coming from and where are we going then. Then the Milky Way is a typical galaxy that we see in the universe. So it makes sense also to be able to study this. Also, it is the only galaxies for which we have a full dynamical component for individual stars, especially thanks to Gaia. We have proper motions now. So it means that it's the only galaxy on which we can really probe in detail the galactic potential in such a detail. Secondly, with this, as I was saying, we can also explore, so we can trace the dark matter with the dynamic of the stars, but we can also explore the nature of the dark matter, and especially what is the temperature of the dark matter particles. Because as you can see here from this plot from a paper from Selim Bohm, you can see that in colder dark matter, the dark matter can condense its smaller structures. And so you have a more clumpy or more granularity in the dark matter component itself than in a warm dark matter, than with warm dark matter, for example. As you can see here, you see clearly that you have less substructures. So here, if you are able to measure the granularity of the halo, you have also really strong indication about the nature of the dark matter itself. So for a long time, people were studying the Andromeda galaxy to studying the stellar halo. The advantage being that you have an external point of view. So you just need to take a few pictures of the sky with a nice telescope to be able to see the stellar halo of the Andromeda galaxy. For the Milky Way, the problem is actually that we live inside, which means that if you want to study the stellar halo, you need to observe the full sky at really high depths because you really want to go really far away. And for that, you need large photometric surveys. And there is not plenty of them. So now I'm going to speak about mostly optical surveys, because if you take the maximum of the luminosity of the stars in our galaxy, especially in the stellar halo, they fall in the optical bands. So in the northern sky, everybody know about the SDSS. That used to be a really big survey covering 14,000 square degrees in the full optical range, ranging from the U band to the Z band. Then it has been replaced or upgraded by pan-stars 1, 3 pi, which cover 3/4 of the sky, but in the G, R, I, Z, and Y band. So you see that it's missing the U band, and I'm coming back after. The U band is extremely important. In the south, we have DES covering 5,000 square degrees, also in the G, R, I, Z band. Then you have some smaller surveys, but really deep. The strategic Subaru, the IP Supreme Cam strategic Subaru surveys. You have Gaia as well, which is not only an astrometric surveys, but provide also really accurate photometry. And in the south, in the future, in the near future, we are going to get LSST, but going to cover the U, G, R, I, Z, and Y band over the full southern hemisphere. So as I was saying, we are missing a deep U band because unfortunately in the northern sky, because unfortunately SDSS is not extremely deep and the U band is not really accurate. So you cannot use the full depth of the other bands with the band of SDSS. And you see actually a lot of different features that appears there. So in that optics, we constructed a new surveys starting in 2014 called the Canada-France Imaging Surveys that was planned initially as a follow-up in the U1 airband for the Euclid telescope in the northern sky. And the plan for Euclid was especially to use these different bands to get photometric redshift. So there was plenty of other telescopes in the north that going to complement this CFIS, especially in the G band. It will be the Raval-Hombre telescope with the JEDI-G program. For the I and Z band, it will be Pan-STARRS telescope and no Subaru. So the thing is, each of these different surveys get an agreement with Euclid, but didn't get any agreement between each others. So we cannot really use the full power of these different bands otherwise than just with Euclid. So it has been decided to get an MOU between some of these different surveys. And right now we have an MOU called UNIONS, which stand for Ultraviolet Near Infrared Optical Northern Sky Survey, which regroup the CFIS survey, Pan-STARRS, the telescope, not the 3 pi survey, something different, and the WISHES survey, which is a survey made in the I and Z band that recently have been joined by the HSC to join the UNION program. So the UNION MOU, maybe you know it as the Northern Sky Alliances, but we realized that the acronym was NSA, so we decided to change the name. So officially, yeah, it is UNIONS now, and we hope that in the future, we will also be able to have JEDI-G surveys in this MOU, which will also give a unique opportunity to the Spanish community to access this MOU, which can be seen as equivalent to the LSST in the north without the time domain, obviously. But otherwise, in terms of image qualities, in terms of depth, it is something which is extremely equivalent. So any kind of proposal or ideas that you think you will be able to implement with LSST, you can already implement it with UNIONS. So now I'm going to focus much more about the CFIS, which is a survey that I've been using a lot. That's actually part of the reason why I moved to Canada. And CFIS is composed of 2 different surveys, or surveys in 2 different bands. A U-band survey is covering 10,000 square degrees that you see in blue here in the northern sky, avoiding also the galactic disk because there is too much extinction, so it's kind of useless in that region. And also airband that will cover a really deep airband that will cover 5,000 square degrees at the end of the surveys, which is a big contribution and required really high image qualities because it's used mostly for the weak lengthening. So you need to get really high quality. So I think that the minimum requirement, if I remember, is of 0.8 of CM. So for the moment, here is the coverage that we are covering in the CFIS U-band. So in purple, it is what we aim to observe at the end of the surveys. And in green, it is something that we have already observed. So normally we should have already finished the surveys, but unfortunately we have been extremely unlucky with the weather. We had on the Mauna Kea some of the baddest weather since more than 40 years, and CFIS is there. So it has been extremely hard for us to observe because we need a really good condition to get these really nice images that I'm going to show you later. So we have been, we get bad weather. We get also a volcanic eruption at some point that stops this. We get problem with the camera, megacam being starting to be quite old now, and also with COVID, obviously. So yeah, so for the moment, the survey is still continuing, and we hope that soon we will have finished the surveys to get the full coverage that we were aiming for. So here it is, the comparison with CFIS with SDSS, and just to show you how significant in the improvement between these two different surveys. So you can see actually in the background the triangulum M33 galaxy that have been stacked with the airband actually, which is made in that cases with the LSB reduction. So we aim also in the future, in the really near future, to detect low surface brightness galaxy in other galaxies. And also it's also really nice to see the improvement, especially in the U-band, when you see the Leo P dwarf galaxy. So Leo P is a star-forming galaxy, so that's why it's popped up really well in the U-band, which is close to the ultraviolet. And you see clearly the improvement with SDSS. So this is made possible because CFIS is 3 magnitudes deeper than SDSS, but also more precise. One of the things also for people that really like globular cluster and CMD like me, you can see also the improvement on the color magnitude diagram of the globular cluster, where if you do a U minus G Gaia against G Gaia, you see here the SDSS color magnitude, and here you see the CFIS U-bands, and you see clearly a big improvement in terms of precision. And actually the scatter is almost similar to HST, which is pretty great actually, because in some globular cluster, you can see the molecular line in the giants. Through there might be also some problem with crowding in our surveys. So with that, we can study really well in detail the stellar halo. One of the things which is the most easy to get for the stellar halo is just to get the density profile of it. It is important to get the density profile of the smooth component of the stellar halo. So you neglect in that cases the substructures, and you just measure what is the slope of the stars in the halo to try to get the profile of it. And then when you have it, and with kinematic measurement, you can go back to the mass at different radii using the Boltzmann conditionless equations. So for the stellar halo, as I was saying, most of the stars are far away. Stellar halo is ranging from 20-ish kiloparsec to 300 kiloparsec. So unfortunately, Gaia is not precise enough to measure directly the distances of the stars in the halo. Even at the end of the surveys, Gaia will be able to provide distances up to 10 kiloparsec, something like that, with good measurements. But behind that, you need to find other technique to get the distances of the stars. So traditionally, what has been made is to search for stellar candles that are bright, easy to identify, like aerial rays. So stars in that case are detected through the variation in the luminosity. So we don't have this in CFIS, but surveys like Pan-STARRS or Gaia can do this. It will be also possible with LSST. Or you can also identify other stars easy to identify, like blue horizontal branch stars, that are stars that are apart from the horizontal branch. So the magnitude is pretty well known, the absolute magnitude. And also they are easy to identify. This is A-type star, so this is present in that coma shape here. And the U-band in that case is extremely important because it helps us to remove contamination from white dwarf, but mostly QSOs that will otherwise make your sample impure and with a lot of contamination. So it's easy with a color diagram to just select that area, but actually in that area, you're also populated from other type of stars called blue strikers. And here you have the spectra for BHBs in red and of blue strikers, of BHBs in blue and in blue strikers in red. And you see clearly that here you have the Balmer jump, which is really typical for these odd-type stars. And actually, the U-band and the G-band can help you to disentangle from the BHBs and the blue strikers. But also the Z-band is extremely interesting because you have the Paschen line. And actually, the Paschen line is sensitive to the gravity. And blue strikers are considered as dwarf stars with a high surface gravity, when blue Rosetta branch stars are giant stars with a low surface gravity. So actually doing different color like U minus G, G minus R, and I minus Z, you can disentangle really well BHBs from blue strikers and get a really pure sample of BHBs. So we did it, and we just measure what is the slope of the stellar halo, taking into account that we have to deal with the completeness of the surveys, especially in the Z-band. Oh yeah, I forgot to mention, so we use the U-band of CFIS and the GRI-Z band from the Pan-STARRS 3-pi survey. So the survey that covers the 3/4 of the sky, which overlap with the first CFIS area. And so at the end, you have 5 bands that are really similar to what will be for LSST. So I measure the slope of that, and it is represented here by a broken power law. So what you can see is we have a break around 40 kiloparsec. And contrary to what have been found in the past, especially using SDSS, where there was a clear drop in the density after 60 kiloparsec, we didn't find any clear cut or any drop in the density. And actually, what we realized is that in the outer halo, it seems that the slope of the profile of the stellar halo is shallower than in the inner halo, which can be the signature of a massive accretion event, like the Gaia and Cebus sausages that you might hear, I have here, which is a massive accretion that occurred a few 10 giga years ago. So what you can see also is that the profile is really similar when you compare to giants or K-giant in generals, where some differences here, but it might be to completeness, also some contamination maybe. So, but otherwise, in average, the slope is very similar. However, if you reorganize this, it's what have been made by the team of Fukushima. You can see actually that you have 2 different areas. So an area covered by the aerial arrays with a really clear drop, which is almost constant up to 150 kpc. And you have the BHBs for which deep surveys such as CFIS and the Subaru strategic program show that actually behind 40 kiloparsec, the slope is different than the aerial arrays with something which is more shallower. And it is really interesting because these 2 populations are characterizing by population of metal poor on old stellar systems. So naively, one will expect to get a similar slope between these 2 different stellar populations. However, as you can see, there is a clear difference in the outer halo. So the question is that something which is an artifact due to a problem in selection? Aerial arrays, you rely about the light variation. So maybe we didn't take this into account. Like when you go really far away, you have more uncertainties, so it's harder to detect aerial arrays. For BHBs, you can have more contamination from blue strikers. Maybe we didn't remove them correctly, so it's possible that we have these biases. But maybe the solution is just that actually these populations are different and they have different origins. The problem of this is that these 2 different populations, whether BHBs or aerial arrays, are really sparse. We're just picking of a few 50 stars beyond 150 kpc, for example, for the BHBs, covering 5,000 square degrees on the sky. So you can see that the density is really low. So when you try to determine the density, actually here you have a lot of uncertainties. Plus you have also to deal with the completeness of the surveys. So it's not necessarily something which is measured precisely, and in statistics, I've seen better feature. So the answer in that case, if you just say, well, there is plenty of other stars, you have all the RGB stars from the red giant branch, why not to use them? So, and also the idea would be also to measure the metallicities, because maybe there is some basis with the metallicities. So in that case, the goal will be to get the free chemical distribution of the Milky Way, as did Mario Ivezic here, where you see clearly the variation in metallicity corresponding to the disk and then to the halo up to distances of 12, 13 kiloparsec. So to do that, what you need is to get the distances of the stars and the metallicity. You would like ideally to get spectroscopy of that, so you can get precise spectroscopic metallicities. However, getting spectroscopic observation is costly, and so at the end you are incomplete. So in that case, what you really want is to be able to use photometric metallicities and photometric distances, so you can assume that you are complete until a given distances, and so you can really trace in detail the three-dimensional chemical distribution of the Milky Way, so the profile density, but also the metallicity in it. And so really quickly, you're going to see that the problem is actually first to know if a star is a dwarf or a giant. Indeed, when you try to do this measure, it's what has been done by many people in the past, was to measure the photometric metallicities using especially the U-band, because in the U-band, you have a high density of absorption line that are sensitive to the metallicity. So you can use color diagram, such as here, U minus G, G minus R, to detect the spectroscopy and build a polynomial model on it. So then you can estimate from the color diagram what is the metallicity of the stars. So for that, you have to assume an ages. So in the halo, we assume that it is mostly all population of 10 to 14 gigayears. And also you have to assume actually that you are main sequence stars. Because when you have the metallicities, you assume your ages, so you finish with a single stellar population, something similar to this. And then you just go back to the color of the stars and you say, okay, it is a main sequence stars, so this is this absolute magnitude there. And when you have the absolute magnitude, you compare to the apparent magnitude and you get directly the distances. Easy, right? Problem is, you don't have only main sequence stars, even if they are the most numerous. You have also some giant stars above there, and the absolute magnitude is extremely different, which means that actually you do a mistake on distances for them of several order of magnitude. And it is on this difference of magnitude between dwarf and giants is higher if you go in the redder color. So one of the ideas, and it's what did Mario Ivezic, for example, was to do a cut in color and to limit where the differences between dwarf and giants is the lowest. And also just to select the main sequence stars mostly. So you can just assume that all the stars are main sequence, you have few giant contaminations, and just measure it. The problem doing that is, first of all, as I was saying, you do an error on distances for some of the stars. You also get an error on metallicity, actually, because the metallicity track for giant and for dwarf is different in the color diagram. And also, you don't use the full power of the observation because you are limited in that cases by the magnitude range cover of the main sequence stars. And if you avoid the giants, you cannot use them to go really far away. So for example, in CFIS, if you just use the main sequence stars, you can reach up to 30 kiloparsec, so just 10 kiloparsec outside the start of the halo typically. But if you use the full power of the giants, you can go up to 100, 150 kiloparsec, and even more if you are able to go up to the top of the red giant branch or to identify them. So to do that, I developed a method to use the full power of the photometric bands that we have. So the U, G, I, Z band and the Gaia G band, to first identify the stars to know if this is most likely a dwarf or a giant, and then for the two of them to get different pipeline to measure their photometric metallicities, and then the absolute magnitude using different method of machine learning. So here we limited ourselves by the Gaia G band. The reason is I'm a dynamicist and I need to get proper motion. So I didn't want it to explore more in detail at deeper magnitude, which would be possible, but actually really quickly we'll be limited by the Z band magnitude, which is a depth pretty similar to Gaia actually. So, and the Z band is extremely useful to be able to disentangle dwarf and giants. So this thing worked really well up to the Gaia magnitude, but then deeper we don't have enough good observation yet to be able to do this and to extend it. Anyway, So this pipeline that I made will be able to be used on LSST because the bands are really similar actually. The U band in terms of transmission is pretty similar to what we have or we will have with LSST, and the other bands are really similar to what will be also produced soon by them. So for the classification dwarf giants, I use a random forest classifier. The reason is it's easy to get the information from it. A random forest classifier, if you don't know what it is, it's just a suite of questions, which is the stars between that color and that color? Yes, no. Then you do a succession of questions. You do that for many trees, and at the end, you will be a probability to get a dwarf or giant. So for that, you need a training sample. And in my cases, I use a Segway surveys as training sample because Segways are surface gravity, so you know if stars are dwarf or giant. So you just train this, and when you have trained it, just using the photometry as input of your random forest, you can use that to all the stars for which we don't even have spectroscopic metallicities, and you can already get a probability for each star to know if it is a dwarf or giant. For the regression, as the metallicity or the absolute magnitude, we used artificial neural network where the input are against the colors that you obtain with this different combination. And in each of these nodes, you're just going to do a linear regression of type A, type X plus B. So you do that for different layers. And the goal is to tweak the A and B of the different nodes to be able to recover the metallicity or the absolute magnitude of your training sample. So actually, you see that if we just do this, just the A type X plus B in each node, you finish with a polynomial, with a big polynomial of order of the number of layers that you have. So it's just actually a linear regression. So to be able to get something non-linear in machine learning, we use what we call an activation function, which is this type of different function, which put on each node that you will be sure that you are not on a linear regression, so you have more flexibilities, I would like to say. So at the end of the pipeline, here is the results that we have. If you take from the dwarf and the giant, in the training sample, initially we have this different fraction. So we are largely dominated by the dwarf. 86% of the stars in our training sample are dwarf, 14 are giants. And if you take the completeness and purity of the dwarf, you can see it's 96%, 93% of purity. Sounds pretty good, but actually it's not really surprising, because if we get a completeness of 1, if we're saying that all the stars observed in the training sample are actually dwarf, we'll get a completeness of 100% on a purity of 86%. So it's much more actually interesting to see the giants because they are minority. In such cases, you see that we have a completeness of 60% of the sample, which means that we cover almost 6 over 10 giants of the training sample. And we have a purity of 70%, which means that on the 10 giants that we cover, only 3 are actually dwarfs. So it sounds not really great, but you have to recall that we just use broadband photometry. And in the past, people were thinking it was impossible to do this classification. And actually, if you go more in the detail, you can see that the completeness go up to 80% for metallicity lower than -2 for the giants, and the purity go also up to 80% as well in that cases. So the conclusion of that is for metal poor stars lower than -1.2, which is the large majority of the halo, we are able to do a correct classification. True, we know that there is some biases in that cases. So you have to keep them in mind when you do this kind of technique as well. For the metallicities, we find something of 0.15 dex for the dwarf, 0.17 dex for the giants, which is pretty similar to what have been done in the past. But with the method that we have, we can go at deeper magnitude, and we require less precision in the photometry in the different bands, because we use more bands in general. So you have more data, so you can get better precision at the end with more uncertainties. For the distances, we get something which is similar than what have been done in the past, so 16% of precision of the distances for the dwarf, which is something which is correct. And for the giant, we get something of 25%. The reason is for our training sample to get the distances, we use Gaia data, and there is not plenty of giants of the halo representative with Segway as well in Gaia with good precision. The reason is for a given apparent magnitude, stars that are dwarf are actually intrinsically less brighter than the giants. And so which means also that they're closer than the giants at a similar apparent magnitude. And so the parallaxes of the dwarf is more precise than the giants. So taking invertly, you have less precise measurement for parallaxes for the giant and for the dwarf. So that's why also our training sample reflects this, just because we lack of data. So that's why I hope in the future that with new spectroscopic surveys that go deeper, that are more representative also of the halo, and that we'll have more stars, we will be able to get better distances, also with using the Gaia EDR3. So here it is, just to convince you that what we have actually is not something which is crap. Here it is when we use our algorithm to reproduce the distances or the color magnitude diagram of globular clusters present in CFIS. So here you have the color magnitude diagram using the distances from the literature for two globular clusters. Here you have using by inverting the Gaia parallaxes, which you should not do for stars that have really bad precision on parallaxes. It's just to show as comparison. But in that case, if you do that, you introduce a lot of biases. So actually, it's what you see. And here it is, the color magnitude diagram that we predict at the end with our machine learning. So you see that we don't detect any of the subgiants just because we don't have a classification specifically for them. I mean, it's already hard to disentangle dwarf from giants. So adding an extra feature will lead to a classification which is rubbish. So that's why we don't have that part. So that's why there is a gap there. But otherwise, you see that we reproduce really well actually what have been made in the literature, which tend to confirm that the distances that we have is pretty accurate. So with this, we produce a catalog of 21 million of stars with photometric distances of metallicities, which is the largest catalog of that type on the market currently. And with that, we have been able to produce a map of the galaxy. And when you compare to the map that I was showing you before of Mario Ivezic, you see that we can clearly extend it to larger distances. So you see clearly again the disk and then the halo with a decrease of metallicities. And you see here a big green arc, which is actually an artifact due to the cut in apparent magnitude that we have intrinsically due to the Gaia surveys. And yeah, so the reason is for a given apparent magnitude and similar color, you will get a higher absolute magnitude for metal-rich stars and for metal-poor stars, which means that you can detect metal-rich stars at larger distances than metal-poor stars. And here, since we are showing the mean of this at different distances, you actually at some point going to get an artificial increase in metal-rich stars just because we don't detect metal-poor stars in that distances. So the fact also that we extended here so far is because we are able to identify giants. So you see clearly the advantage to be able to probe the giants. So with this catalog, we aim to do many things in near future. And for the moment, it has been used to be able to detect new stellar streams, especially stellar streams emanating from the globular cluster M92 that we discovered last year. So we did, using our catalog of dwarf and giants, help us to complement another study that we did using match filter to extract the signal and to confirm the existence of the streams. So this stream has a really nice properties. We have been able to measure from giants and from the match filter that the mass of the stream is equivalent to 10% of the current mass of the cluster, and it's emanating from 17 degrees, it has a length of 17 degrees from M92. And using simulation, we have been able to study the dynamical ages of the streams, and we found that the streams is really young, less than 600 million years ago, which is extremely young, especially when you compare to the age of the actual cluster, which has an age of 11 giga-years. So it's forced us to wonder what is the origin of this cluster. Or is it possible that such old structures is just starting to be destroyed pretty recently? Where was it for the last 10.5 giga-years? And so many hypotheses are possible. Maybe it is a core of a dwarf galaxies that has been destroyed, and we just see now the residue of the core of it. So maybe there is a more fainter streams along the orbit of this. Another thing will be that the globular cluster was actually part of orbiting around the dwarf satellites, and the dwarf satellite is now completely disrupted. but the dark matter halo of this one was protected the globular cluster for many giga years from being completely tabulated disrupted. Another thing also is because the globular cluster is passing in the inner one central KPC of the Milky Way, it's also possible that its orbit has been modified recently by, for example, the galactic bar that could have modified the orbit of this one, but also its morphology. So in near future, with more observation of this stream, with better simulation, with more detailed simulation, we will be able to probe the galactic potential in the inner galactic potential of our galaxy. So for me, it's really interesting that an object which is at 8 kiloparsec from us can help us to, in the outer part of the galaxy, can help us to probe the galactic potential in the center of the galaxy. So for example, with that, we can also probe the dark matter, the black hole masses, the modification of the gravity also due to Einstein equation in that cases. So there's plenty of things that we can do with this cluster in near future. So we just need to get more observation, especially spectroscopic of it. Another one that we not discovered in that cases, but extended the discovery is streams emanating from the globular cluster NGC 4466. And in that cases, contrary to M92 that will help us to probe the inner potential of the Milky Way, this one has a large apocenter up to 45 kiloparsec on a pericenter of 10 kiloparsec. So we're not really going to be able to probe the inner part of the galaxy, but we can probe the galactic potential in the outer part of it. And the reason is that the total amount of energy of the stars along the stream is conserved. So it means that if you're able to measure the velocities and the position of the stars along the stream, you can go back to directly the measure of the potential, of the energy, and then of the potential. So interestingly also so using the dwarf and giant, one of my students, Jacqueline Jensen, which is going to submit really soon this paper, normally this week, has been able to use the giant and to do some proper motion cuts, metallicity cuts, and distances cuts to identify the stars of the stream. And we will be able to see that there is a strong gradient in distances along the stream that didn't have been observed before, with distances ranging from 10 to 30 kiloparsec. So one of the things also that we will be able to see soon is the impact of the LMC infall. Recently, it has been proposed that the Large Magellanic Cloud is really massive, with a mass ranging from 1 to 3 times 10 to the power 11 solar masses. So which means that at the distances of the LMC, it's almost a quarter of the mass of the Milky Way in that radius. Which means that in that cases, you have a lot of perturbation introduced by such a massive object. First of all, you have a dynamical friction tail produced that is going to break the dwarf galaxies due to the passing in the dark matter halo of the Milky Way. But you have also a collective response, which is mostly due to the attraction of the Milky Way by the LMC, which means that actually you have a shift of the barycenter of the galaxy, which lead to these collective responses. So it has been predicted for simulation that this perturbation in the dark matter should also lead to perturbation in the stellar density, either behind the LMC, especially at the distances of the LMC, you can see the dynamical friction tail, but also at larger distances, you can start to see this overdensity due to the global motion of the stars in the halo due to the collective response. So we hope that we'll be able to do that with CFIS soon, and also LSST will be crucial to get fully the halo perturbation. So the reason that I said we will be able to observe with CFIS is even if we don't cover the LMC, you can see that we have a part of the surveys that actually going to cover the end of the tail, but also because we are able to go very far away, we start also to be able to see the global response of the halo up to 70 kiloparsec or 100 kiloparsec. So so with CFIS on unions, we'll be able to start to characterize it. But if you need to get a full view of the impact of the LMC and to characterize it fully, you need also to get the complementary observation that will be provided by LSST. So we hope that when LSST data will be available, we'll be able to apply the same methodologies that we have been using on CFIS union data to make such a photometric catalogs and to study the density of the Milky Way. So one wonder also what is the impact of the Sagittarius on our galaxy. So the same group of people that did the simulation of the LMC added a massive Sagittarius dwarf galaxies, which is the third most massive dwarf galaxies after the LMC and the SMC around our galaxy. And this group of people shows that the Sagittarius dwarf galaxies doesn't play a dominant role in perturbing the halo. However, we show with CFIS that the Sagittarius has a strong impact on the disk, especially on the vertical elevation of the disk, because the Sagittarius can actually explain the flare, the really high flaring of the galaxies that we have been observed using those triggers identified in CFIS, because we observe that the disk can be seen actually up to 25 kiloparsec and with an elevation of 8.5 kiloparsec, which is really high. And this also is consistent with the observation that Sagittarius has an impact, or seems to have an impact, on the star formation history of our galaxies, as shown by Thomas with Lara on Carme here, that actually Sagittarius, when it goes to the pericenter and passes through the disk, can actually boost the star formation rates of the galaxies, as you can see on that plot. So Sagittarius doesn't play a dominant role in perturbing the halo, but have a really strong impact on the disk. So another reason to study the stellar halo is actually you cannot really decouple fully the disk from the halo. We have to study the Milky Way in its globality. So as I was saying, I'm going to finish quickly on this. I'm a dynamicist, and know with large photometric surveys, we can get distances. With Gaia, we have proper motion, and with distances on proper motion, you can get tangential velocities. Unfortunately, we lack radial velocities for most of the stars, and so that's why we still need expensive, deep spectroscopic surveys. So you have plenty of them that are planned for this decade, such as Foremost or DAISY, but I'm mostly going to focus on WEAVE, because I'm here actually at the IAC to work a lot with WEAVE, and also it's something local, so it's pretty interesting. So WEAVE is a survey that is going to cover 10,000 square degrees in the northern sky. A big part of that will be the stellar halo, actually. It has a large field of view with 2 degrees diameters field of view, with taking 1,000 spectra at the same time in high resolution and in low resolution mode. So actually, it is a perfect tool to be able to do galactic archaeology, because we'll be able to get metallicity, alpha abundances, and radial velocities with low resolution, and individual abundances in high resolution. So which means that we can really probe the nature of the progenitors of our galaxies, but also to get information that we are lacking so far about the kinematic. So we will be able to probe the galactic potential. So especially for the galactic archaeology sub-surveys, you have a big component that will start to observe the stellar halo. And we plan to start the observation of WEAVE this year, likely in September. And one of the ideas will be especially to cover the stellar streams, to get more radial velocities of the stars of the streams, because we have been able to identify a lot of structure recently, especially thanks to Gaia, a lot of stellar streams. However, we are lacking radial velocities for most of the stars. Here we have a map of the stars with radial velocities, which is shown by the color point. And you can see that actually we don't have a lot of radial velocities. Like here, you just let the point up pretty big of the overlap. But in total, we just have 600 stars that have radial velocities in the streams, which is not a lot actually if you want to really probe in detail the galactic potential, and so to probe the galactic potential, also to get the math of it. Also, as I was saying, we'll get individual abundances, we'll get alpha abundances. So we'll be able to probe the star formation history of the progenitors, to probe the nature of the progenitors. For some of the streams, it is unclear if the progenitor was a dwarf galaxy or a globular cluster. In that cases, alpha abundances, especially magnesium and nitrogen, are going to help us to characterize the progenitors. And also, we will be able to measure the granularity of the halo, and I'm going to finish on that. It's that along the stellar streams, you can have a passing of a dark matter subhalos that are going to pass through the streams, and which is going to make under density as you. Oh, okay, the video doesn't work today. So normally here you have a video made by Denis circle, where you see the stream with a dark matter subhalo passing through, creating the densities. So people were thinking it would be possible to use deep photometric survey to study this, and so to get a measure of the granularity of the halo. However, we show that some of the gap variations that have been observed along some stellar streams, as the Paloma 5 or GD1, are actually artificial due to the incompleteness of these large surveys and due to the inhomogeneities. Remember that for the large surveys, it's taking over several days with different observation conditions, and you really need to take this into the detail when you compare simulation to observations to really probe this. So in that case, is a better way to study the perturbation produced by the subhalos is not by the density variation along the streams, but by the kinematic perturbations of the structures along the streams. So it is also part of the plane of WEAVE. And also, yes, WEAVE will help us also to identify new substructures, which is not spatially coherent. So things like are completely destroyed that are not stellar streams anymore, but as are still visible in the phase space, like you have here with the Gaia-Enceladus sausages, which is this probe of the massive accretion. And so with WEAVE, we'll be able to get more stars, so to be able to probe, to find more sign of accretion, but also we will be able to relate some of these objects together, because it has been assumed, for example, that the sequoia, which is thing to be the sign of a massive accretion 10 giga-years ago, but different than the the Gaia sausages, sorry, could actually be part of the Gaia sausages, as shown by Ingrid Jean-Baptiste, where she shows that a massive galaxy accreted a few giga-years ago can reproduce something like the Gaia sausages and Enceladus, but also the sequoia, just because you have the dynamical friction that breaks your progenitors, and so you have a loss of energy on transfer of angular momentum to the halo itself. And what is really interesting is actually that this prediction has been made before the discovery of these two objects. So yeah, it's pretty interesting. So yeah, I'm really finishing on that. It's just that also with spectroscopic data, we'll be able to get more precise distances. And I'm the creator of the principal module to get stellar distances for WEAVE. The advantage being compared to what we have with just photometric data is that we have precise measurement of metallicities and surface gravity. So you can really get precise distances. And I'm just showing here the results that I'm just obtained really recently, applying a similar pipeline that what I was showing you before, but on spectro-photometric data, tested on the segue spectra. And here it is the color magnitude that you expect that I give to the machine learning. And here it is a prediction. So not only we are able to recover it, but actually we are able to improve the color magnitude diagram. And you see really clearly, for example, the double sequences here in the main sequence stars, which is not visible if you just use the Gaia parallaxes. And this is actually something that have been observed, and we just improve the measurements. So for the moment, we have a precision of 13%. I think this value is overestimated. I think we are more precise than that, as you can see here. And also with spectra being with slightly higher resolution and likely of better quality of segue, we hope to even get more precise distances. So here is my conclusion. My conclusion is we still have plenty of work to understand galactic history and the galactic dynamic in our own galaxy. We have discovered a lot of plenty of new structures, but we are unable to use them fully for the moment because we are lacking spectroscopic surveys. So far we need precise distances. This is a key element to be able to study our history. And also we need spectroscopic data to get metallicities, to get velocities, radial velocities, and alpha abundances. So we'll be able to find new substructures to probe the galactic potential at different scale, and also to measure the dark matter nature, especially to know if it is more cold dark matter, if it is a warm dark matter, or if you need also paradigm like modification of the gravity or things like that. Well, thank you really much.
All right, Guillaume, thanks to you for this very nice talk. So this is question time. So I would encourage people to raise their hands in case they want to ask any question. So far, I see no no hand being raised. Here's one. Okay, this is from Karma. Okay, just give me a second and I will allow you to, yeah, solicitar. No, you should, Karma, you should be able to speak now, to unmute. Can you speak now?
Yes.
Okay.
Hi. Okay. Could you go back to the, well, first, thank you for the very nice and comprehensive talk. Could you go back to the plot where you show the profile of the halo, where you said that it will be shallower at large distances? And could you explain that? Because I didn't understand it well. If it is, I mean, how do you see that it is actually shallower? Yes, or the previous one, maybe. I don't know. Yeah.
Okay, so this previous one, it's kind of hard.
Yeah, go ahead.
Yeah. So for this one, it's hard to see actually that the profile are different. The values that we have are different, but the plot is not the best. I was just, when I made that plot at that time, I was trying to spread the best as possible the different slopes, so you can really see that. And actually, I prefer that plot that had been made a year after on a paper from the Japanese team, where they regrouped in terms of density of raw density in that cases, BHBs and aerial arrays. And you see that all the stars that are aerial arrays, which is in this non-blue color, have very different profile than these blue colors that are the BHBs, especially beyond 40 kiloparsec. So that's why we are struggling, because naively we will have expect to get the same profile, because aerial arrays and BHBs trace the same population normally. So this is tracer of metal pool, all stellar populations. So that's why it's interesting to see these differences between BHBs and aerial arrays.
But regardless of the difference, you talked about a change in the profile around 4 kiloparsecs.
40, yeah.
40?
Yeah, around 40 here, yeah.
And how do you see that?
So here actually you see that the profile is steep and then it starts to be shallower.
Okay, so is this a slight difference? Okay,
yeah,
so
exactly.
it's a very slight difference.
Yeah.
Okay.
Well, actually, it's not so much different, because here we have a slope of almost 4 in terms of power slope. You have a slope of 4, and here of 3. So actually, the difference is pretty significant. And we think it might be due to the big massive accretion like Gaia sausages, which the stars on a really radial orbit will have an apocenter around 35-40 kpc, which have been predicted or analyzed by Alice Decent in a really recent paper.
Okay, so it would be the pileup of the stars of this accretion.
Exactly.
Okay.
Yeah.
And
so it will be the profile of the halo before this accretion and then after this accretion, or the contribution of the normal halo made by the normal accretion of the galaxies. And in that case, it will be the normal halo of normal galaxies plus this really massive accretion.
Okay. Sorry. And then if you could, the last question, if you could go back to the Sagittarius slide. So you have used the circular velocity to select stars likely belonging to Sagittarius, and then in the lower panel.
So it's not,
sorry,
sorry, I didn't explain it really well. So we use Bush Trigger stars because they are more, they are intrinsically brighter than main sequence stars, so you can observe them at larger distances. And using Gaia proper motion on Segway radial velocities, we just identify the circular velocity component, which is actually starts from the disk, and we just observed a flaring of the disk, which is something that we know. So we know that the disk is flaring, but for us, because we are able to go really far away, we were able to see that the flaring go up to 8.5 kiloparsec at 25 kiloparsec. And because it's covering mostly the apocenter, we were also able to identify just stars in proper motion in the southern hemisphere where there is no Segway spectra, and we go again up to 25 on similar altitude. So here is a story. I arrived at some point in the office of Xavier Laporte, showing him, and he just told me, oh, look, I have this simulation taking into account the Sagittarius, and we have the same flaring. And then we compare with other simulation without Sagittarius, And with the radial migration, you are not able to explain actually this elevation of the disk naturally. You can go up to 3 kiloparsec, but not so high. To really do this, you need to get the Sagittarius passing through the disk on repeated passage, hitting the disk, and so you have some stars that are kicked outside from the disk and making this flaming of the disk. So that's why we are able to see the signature of the Sagittarius directly of the disk without observing the Sagittarius.
Okay, so if I understand correctly, you would expect some flaring of the disk without Sagittarius, but not as much as observed.
Exactly, yeah.
Okay.
Exactly.
Thank you very much.
Thanks to you, Carmen. There is another hand raised by Mark. Mark, you should be able to unmute now.
Yeah. Hello. Thanks very much for this talk. I wanted to go back to the question of the density profile of the halo that Carmen raised before. First question is, how do those slope compare to like a Navarro-Frank-White profile? And the second question is, how spherical are you finding the distribution, or are you assuming the distribution to be more spherical, centrally symmetric? I'm thinking at 50 kiloparsecs, 100 kiloparsecs, you are in a region where well affected by the orbit of the Magellanic clouds, and so it could well be that half of your in one side of the Milky Way, the profile is extended, while in another part it is compressed. So it is like a radial M1 asymmetry.
Yeah.
Do you have data on that, or do you have assumptions made about that?
Yeah. So compared to the Navarro-Frank-White profile, so Navarro is a NFW profile has a slope of 2 to explain the circular velocities. So this one is a slope between 4 and 3. So it is actually a steeper profile, which is seen in every other galaxies that we have so far. So on other galaxies, you have an extra point of view. So it's actually easier to get the profile, just because you can just assume that some symmetry, and you just measure the number of stars at different radius. And actually, we always seen a slope which is steeper than in the NFW profile, which is not completely surprising, because when you have a dark matter galaxy, the dark matter is in the outer part of the dwarf galaxies, and this is the first component to be stripped. So it's normal that the stripping is starting in earlier moments than the stellar component itself. The stellar component will be accreted at shorter distances, especially for massive galaxies that sink really quickly in the center of the galaxy due to dynamical friction. Then the second part was assuming the sphericity of the halo. So in our case, we just assume that we have something which is axis symmetric. So we assume a halo which can be either oblate, so like a pancake, prolate, like what would be the shape of, like a balloon that you squeeze, or spherical. And we let actually these parameters free, and we allow some variation with distances. And what we found, and it's also something that has been found for the aerial iris, is that in the inner halo, the halo is mostly oblate, which has the shape of a pancake, which also is likely due to the disk. Some of the stars in the inner halo actually not coming from accretion, but are kicked out from the disk due to the heating of repeated passage of dwarf galaxies through the disk. In the outer part, we found that the halo is prolate. And actually, it's again not something which is unsurprising, because you expect from cosmological simulation to get a triaxial halo. However, as I was saying, this has to be taken with a pinch of salt, because we're just speaking about 50 stars beyond, and maximum 50 stars beyond 150 kpc. So it's already hard to get a profile, so it's even harder to get a correct shape of it. So we hope to be able to find more stars for that. So for the accretion of the LMC, so these studies have been made before this assumption of a massive LMC that really popped up pretty recently. So yes, it is possible that you have this fact of compression, dilatation of the halo, and it is actually what I was showing here. If you got different distances in the inner halo, you don't see any great modification of the halo, except locally due to the dynamical friction tail. But when you go at larger distances, you have what they call this global motion of the halo due to the attraction of the disk or the change of the barycenter of the disk due to the LMC passage. So in that case, you're going to squeeze the halo in the outer part or in the northern sky and less squeeze in the southern hemisphere. So it's something that, yes, we should be able to study. There have been really recently a Nature paper that actually I have here that claim that they discover this. However, the method is really nice. However, there is a lot of uncertainties in the method, especially related to the distances. So again, I will take this discovery with a pinch of salt, and I would like to extend it with more data that we have using unions and LSST in really near future, but also by using spectroscopic data to see not only the density variation, but also the fluctuation that we expect in velocities. We expect actually to show this perturbation in velocity space. So yeah.
Thanks.
Thanks to you, Mark. Any other question? I don't see any other hand raised. Also in the chat from YouTube, I see no comment, no question. I have my own couple of naive questions for you, Guillaume. You know, I'm a cosmologist, so I'm a bit far from this, but you know, I'm participating in these J Havalambre surveys. In particular, I'm participating in the J+ survey, where you may know that there is a narrow band placed at close to the calcium triplet at around 8,100 angstroms. Although it doesn't get too deep, it goes down to 20 or so. I was wondering whether either with J+ or JPass, which would be deeper, this kind of narrowband filters could be of any use for your science.
Clearly, especially it will help us to get metallicity measurements. So it will improve the metallicity measurement, especially for the less metal-rich stars. So we have also, I'm also part of another surveys that I didn't mention called Pristine, which is a kind of a concurrent of CFIS in terms of time, because for us we required good time on CFIS. For them they required snapshot time, which is crap time. And it is a survey which is made around the calcium H and K doublet. And getting this narrowband filter is helping us to get better metallicities, but also when you compare the different bands, especially through non-linear method, through machine learning, you can use all the different bands also to constrain the surface gravity of the stars. So this kind of narrowband around calcium triplet will also help us in the term of classification for dwarf giants, and so will help improve us the distances that we will obtain.
What is the typical depth that you need for such filters?
Well, the better it is, the deeper it is, the better it is. Yes. In our cases, since we want to use a full Gaia depth, it will be great to go up to the Gaia, to be limited by Gaia. So to go up to G of 21-ish.
21.
Yeah. After, if you are at 20, it's good as well. We can go up to 100 kiloparsec. So taking just into account that
then looking at J+ data, we have around public 2000 square degrees. And I'm not sure what is the depth of that filter in particular, but it should be close to 20. Yeah, maybe a bit 19, maybe a bit shallower than that, or maybe 1 magnitude shallower. I have to look at it, but maybe it would be of some use for you. For sure, JPass would be deeper than that. We have to wait for that. Yeah. One silly question. I guess this is crazy, and you're dominated by peculiar radial velocities. Since you have millions of spectra now of stars in our halo, well, in our galaxy, I'm not sure if most of these spectra are, well, I'm not sure how many are them, of these spectra in the halo or in the disk. But has anyone thought of trying to attempt to measure the gravitational potential of the galaxy by looking at by stacking spectra and trying to get the gravitational redshift from the spectra?
Oh, that's a good question. I don't know at all. So for the moment in the halo, I'm almost sure that no, because we just have a couple of 10,000 stars maybe in the halo, etc. With WEAVE, at the end of the survey, we will get almost 500,000 of stars in the hill. Well, so we'll be able to do that. Yes.
And the precision of redshift usually is what, at the order of 10 to the minus 3. What is the typical resolution? Do you know what is the typical error in the redshifts? No.
No.
Well, not redshift. Well, yeah, redshift.
In velocities. Yeah. Sorry, in velocities. Well, in that case, that would be around 3 to 5 kilometers per second.
That's roughly the for one single star, right? That's roughly that's close to what you would expect for the gravitational redshift, right? Maybe maybe 1 kilometer per second, maybe a fraction.
But in that cases, again, the problem will be to get the distances of the stars.
Well, you don't need it, right? I mean, I presume the main contaminator will be the peculiar, the radial peculiar motion of the star with respect to us, right? But if you stack many from many stars from different regions, I would expect that to average out.
Yeah, but you will measure. You will get a measurement. You will get a measurement at a given position, right? So to know the position, you need to get the distance.
Oh, right.
And that's why I mean, like, we're dominated by distances.
Right.
So that's the conclusion that all distances are crucial.
Right. You're right. You need to know how far they are in order to know where.
Exactly.
Okay. All right.
Yes, that's a good idea.
Thank you. There's a new question by Mark. Mark, go ahead, please.
Yes. Just a little small group, but I just wanted to reassure everybody here that we at the Isaac Newton group are working really hard to do the final steps in the integration of WEAVE, and so the next year the surveys can start. So you can count on it, on having an instrument working next year and starting to generate this data set, which I see you're prepared to really exploit. So it's going to be very fascinating for us to start seeing the results of the instrument.
Yeah. So I'm actually the representative of one of the sub-survey at the science working group of WEAVE. And so we aim to start with the first light in September this year. We have been delayed, unfortunately, due to COVID, due to Brexit as well. But soon we will be able to get the first spectra, and that will be a big event for all the IAC, I hope, and even for the European community in general. And then we will be able to exploit it to do, hopefully, good science.
Sure.
All right. Thank you, everyone. Any more questions? We're gone quite beyond the time, but that's fine. This is for a good reason. If not, I think we can. There are people clapping. Indeed. Thanks again, Guillaume, for this very nice talk. Thank you, everyone, for attending and participating, whether regardless you ask the question or not. And see you next week for next seminars. Thank you all. Bye-bye.
Thank you very much. Goodbye.